Welcome everyone to today's Spark webinar. We're going to cover the use of Spark for embedded and systems programming. Please note that this event is being recorded. The link will be available via email after the webinar has concluded. You won't be seen or heard, but if you're not comfortable with the recording, we invite you to log off now. I'm Tony Aiello, one of the product managers at Adacore. I'm responsible for Spark. If you have any questions during the presentation, please use the tab at the bottom right of your interface. We'll answer these questions during the Q&A session at the end. Before we begin, we have a quick poll for you. How many of you have used Spark before? While you complete the poll, let's get started. Before we dive in, I'd like to say a few words about Adacore. Adacore is a tool provider for high-integrity software. We were founded in 1994 and have about 150 employees worldwide. Our technology is used in a wide variety of projects throughout the world. We bring expertise in embedded and high-integrity platforms. We develop tool chains for a growing number of programming languages, Ada and Spark, C and C++, and Rust. Our goal is to be your one-stop shop for high integrity and safety-certified embedded needs. Without further ado, I'll hand off to Yannick Moy, Adacore's head of static analysis and one of the lead developers of Spark.
So hi everyone. I'm going to talk about Spark, which is a technology for program proof, which consists in two essential elements. So there's the programming language called Spark as well, and there's the analysis tool called GNAT-proof. The programming language is derived from Ada and really consists in two sub-languages, one for program specification, what we call contracts attached to program elements, and one for program implementation. And typically, the program specification is found in files with the extension ADS for Ada specification, and implementation is found in files with extension ADB for Ada body. Now, the analysis tool checks the consistency of the implementation with the specification. And because this is program proof, you can be assured that there are no missing errors here. This consistency check is done unit by unit, and inside the units, subprogram by subprogram, and we're going to see now what the contract looks like. So the first line of a contract is just its signature. So we can see here that the procedure do this and that as two arguments, arg1 and arg2 of type C, which are of mode in-out, which means that they can be read and written. And the rest of the specification is made up of these aspects. So these names, global, pre, post, exceptional cases, always terminates, followed by an expression. And all of these are optional. You can skip some of these, and the tool will come up with a reasonable default. So let's look at them in more details. The global aspect introduces the global variables that are read and written by the procedure, so that completes the signature with parameters. And here, glob1, glob2 can be read and written, so that's why there are modes in-out. Then we have the precondition introduced by pre, which states the condition under which this procedure can be called. And that will be checked at each call site. So here, that's the fact that the two arguments, arg1 and arg2, are different. Then we get the post condition, which is a condition which must be assured by the procedure before it returns. So that's a relationship between the input state and the output state. And we have access to all values in the input state thanks to this attribute old. So we can say here that if the two arguments arg1 and glob1 are equal before the call, then we want arg2 to be equal to 0 when procedure returns. And with the latest version of Spark Pro, we can also specify the same kind of relationship in case an exception is raised. So here we have this exceptional cases contract, which states that the procedure can raise two exceptions, constraint error and program error. And the first one only when arg1 parameter was 0 at the call site, and the second only when the arg2 parameter was 0. Also, with the latest version of Spark Pro, we can specify a condition for termination for this procedure. So that's with the aspect always terminates. And we can specify here that when R2 is greater than 0, the procedure must always terminate. So let's look at this in an editor. And I've picked here Visual Studio Code, which is one of the editors which supports Spark, thanks to its Ada and Spark extension. We can see here contracts, which are a subset of the contracts that I listed before. So for example, for the function maximum here, we specify that X and Y must be different at the call site, and that we want on return that the result of the maximum function is either Y, when it's the greater value, or X otherwise. For swap, similarly, we have a subset of the contract. So here in the procedure swap, which swaps its two parameters, we specify that it doesn't read or write any global variable, and that on exits, the two values have been swapped compared to their initial value. And finally, we have exceptional contracts and termination contracts on these two functions, may raise and may halt, which specify, like I said before, a condition under which the exception constrainer may be raised, or the condition under which the procedure here must terminate. So I've implemented these with errors, and so now we can call the connect proof analysis tool through the corresponding task. And so you have the tasks under Spark, which allow you to run the tool from all the program down to a single line. But here we'll use it just to prove a current unit, current 5. So let's do that. And here it comes up with a different number of errors that you can find in the problem view. Problems are reported either in the code. So here that's the case because this loop doesn't terminate in a case where the function, the procedure should terminate, or in the contracts. And here now we can fix these. And if we fix them, we can rerun the tool, which checks that the implementation respects its contracts. So let's go back and consider what are the characteristics of embedded and systems code. In this kind of codes, there's a lot of attention to memory usage. Why? Because for embedded codes, there's limited memory available. And for systems codes, there are limited mechanisms in general for allocating memory. So you're not free to allocate and allocate dynamically any kind of memory. Both may require compact representation of data. In addition to that, the representation of data may be dictated by the hardware. Think of a fixed address of data for memory map registers of I/O. And similarly, the hardware datasheet may mandate the memory layout of data or valid ranges for this data or valid special values. In addition, for this kind of low-level codes, it's quite convenient sometimes to have multiple views, typed views of the same data. So the same data can be viewed both as a byte buffer, say, and a structured list of fields. Now let's contrast that with the characteristics for program proof. Program proof focuses on functional properties. So that might be both absence of negative properties, so absence of errors, think, for example, runtime errors, and that includes memory safety, which is essential for security, as well as positive properties, so checking that the input-output specification of function is respected. With the latest version of Spark Pro, we can also check behavior in case of exceptions and proper termination. The analysis of Spark is highly automated thanks to the use of state-of-the-art automatic provers, but this is enabled by a level of abstraction from the hardware. We wouldn't have the same level of automation if we were to follow how data flows from the memory to registers or how the stack pointer is updated. So the analysis really works not on the actual code that executes, but on a model of the logical flow of control on data. And in this model, the data representation is ignored. One essential part of this abstraction is strong typing. So the same data for proof cannot be both a byte buffer and a structure of fields. So when we contrast these two characteristics of embedded and systems code on one side and program proof, you might wonder if program proof is a good fit at all for embedded and systems code. So that's the case with Spark because we use two techniques. We use separation of concerns and we minimize the contact surface. So for separation of concerns, we consider separately the representation of data related to the hardware and the logical view of the data that is important for proof. The tool checks the consistency between both. Now, there are some cases where the hardware representation has an impact on the logical view. And that's where we want to minimize this contact surface. That's the case in particular with aliasing. That is, when multiple names in the program refer to the same memory chunk. And here, we want to forbid aliasing between pointers that would be problematic and control all the kinds of aliasing between variables through their addresses. In particular, we want to avoid this kind of aliasing to create invalid values. And that's the same for typecasting, so in reinterpreting the same data between different types. Finally, we have other features that help with writing embedded and system code, like facilities for bindings with C programs, different flavors of specification for volatile data that we'll see. So let's start with separation of concerns between the hardware representation and the logical view of data. We can see that very simply on this small int type. So that's an integer type which holds values from 0 to 42. That's the first line, the logical range of values. And on the second line, we specify representation aspects of this type. So it's alignment in bytes, its size in bits, and the size of objects of this type in bits as well. Now there's a consistency check that this hardware representation is valid for the expected logical range of values. Let's see that in Visual Studio Code. So now we have this type small int, and indeed we can analyze this code without any errors. But if we pretend that it can fit in 5 bits instead of 6, then the tool is going to report that it's too small, indeed. And the same holds true for all types. So you can do that on a record type here, which holds 3 of these small ints, whose size can be 18 bits because we instruct the compiler to pack these small integers across the bytes of the record. Same for an array here of 3 small ints, like the record, which can also have size 18 by being packed. We can even have holes in our representation. So there's a syntax here for representing exactly at which bytes and bits each field of the record lays, which allows us to have a hole here between bits 12, beyond this last bit 11, and the next used bit 16, so from 12 to 15, a hole in the type. We'll finish with this representation of data with an enumeration here, protocol, which has 2 values, text and binary. And we can specify exactly which integer value represents on the hardware each of these enumerated values. So that's for representation. Now, for the logical view, we have a lot of power in Spark. We can specify arbitrary properties of types, thanks to the aspect predicates. So now, if we take this special small ints, that's a subtype of the small int that we saw, but with values that can be 0, 5 to 12, 18, or 42. And if we assign a value that is not in this range to a variable x of this type, the tool is going to report that indeed the predicate might fail. Same for more complex type like records, where we specify here that the 3 components of the record are in order, A is less than B and B is less than C. Again, if we violate this condition, this will be reported by the tool on the definition here of the initial value for 1. And you can see that in the problem view. To finish that demonstration, let's look at an array, where here we have these more complex properties that says that for every index in the array, we want the value at this index to be greater than 5 times the value of the index. Again, if we put here a value that violates these constraints, then we get the violation. If we fix that and we rerun the tool, we get no other messages, and we can check that the tool has completed its analysis by going to its data file. So I'll go to that later. So let's go back and now look at how we minimize the contact surface between the hardware representation and the logical view when both intersect. And let's start with aliasing between pointers. So that can be seen very simply on these 6 lines of code. On the first line, we allocate a new pointer to this variable x, and then we assign x to y. At this point, we have created aliasing, that is, the 2 pointers point to the same chunk in memory, which means that when we increase the value underneath this pointer through x or through y, we actually increasing the same underlying memory. So that's something to take into account in analysis. But more importantly, when we dispose of memory, so like we do later with 3 of y and 3 of x, then we are trying to liberate twice the same memory, which is a problem, and which is a problem both for safety and security, as this kind of code in some languages can be exploited to gain access to the remote program. So the problem with aliasing with pointers is that pointer object gives indirect access to the memory, either stack or heap. And in general, analysis has an imprecise knowledge of the exact value of this pointer. In the worst case, the pointer can point anywhere in the memory, with the consequence that the analysis is quite imprecise. We still get guarantees from strong typing in Spark. So the pointer can only alias memory of the same type, and it can only point to either the heap, dynamically allocated memory, or the stack variable that has been declared explicitly with the aliased keyword. But that's not enough. So in Spark, we rely instead of a notion of ownership. We have to follow ownership policy, which means that only one pointer at a given time can has write access to the memory. So let's see that in in Visual Studio Code, sorry. So we have here this code that we showed on the slides. And when we analyze it, the analysis tool reports here that when we're trying to write x, it's neither readable nor writable. Why? Because x has lost ownership of the underlying memory when it was assigned to y. So now, if we remove that, and same for 3, because x is not readable here, now the tool checks that indeed the flow of memory is correct. Notice that if we don't liberate this memory here, the tool reports a possible memory leak correctly, because y is now the owner after the assignment, and that's through y that the memory must be free. So the same holds true with more complex data structures. So we can have here a linked list of nodes. So we have a node here with some data and a next field which points to the rest of the list. We could do that with a loop for lists of arbitrary length, but we'll do this very simply with just a list here of length 3. So with a node 0, which points to a node 1, which points to a node 2. And let's call here head, the start of the list, and node 1, the next node, and node 2, the final node. Let's reverse this list in place. So how do we do that? We make nodes point to heads, node 1 point to head, node 2 point to node 1, and head becomes node 2. So if we do that, the analysis correctly detects that at this point, when we are assigning head as the next node of node 1, head in fact still points to node 1. So we are creating a loop, and if we execute this code, we are creating really a lasso, not a list. So the correct thing to do here is, of course, to set the next field of head to null before doing that. So let's do that. But here, what we didn't do is that we didn't treat the memory. So again, this is reported by the tool. There's a possible memory leak. And if we just free the top pointer and reanalyze, again, something is amiss here, because when we free the top pointer, we're leaking all the underlying memory. So the correct thing to do really is to free all the nodes, and that would be done in the loop if we had the list of arbitrary size. And here, everything is correctly verified. Now there's a different problem with a variable through their addresses. So we can lay out two variables in memory with the same address. That's what we call the memory overlay. And that's typically done to provide another view, type view on the same data. The consequence is that writing through one view will update the other view. But of course, that can create invalid values if not all possible values to one type are correct for the other type. We have the similar problem when we cast values through different types. So that's called unchecked conversion in Ada, but really it's checked in Spark. So what we can guarantee in Spark is that there's a full mapping between the types when we do that they have the same size and alignment, and there are no invalid values in the type representation. So let's see that. So we have a record here with a number of components. We could specify its alignment, size, object size, like we did before. But here, we let the tool call the compiler to get this information. So overall, the size is 64 bits. And we have a buffer of 8 bytes. So with size is also 64 bits. That allows us to do this unchecked conversion between the two types, so from buffer to this structure here, or to lay out buff here as a buffer on top of arg, the argument of this procedure, at the same address. So we can see here that they have the same address. For example, here that allows us to zero out the argument through this untyped view. And when we analyze these codes, indeed, there's no problem. But if we make a mistake and change the size of the buffer, say, to have only 7 bytes, then the analysis is going to report that both for unchecked conversion and for memory overlays, there's a problem of size. Now, if we do something more subtle, is that we change this type here to be only the positive integers and reanalyze. Again, the analysis is going to report that the type here is unsuitable, and you get more detail in the terminal because here the type has only so many values, which doesn't cover the full size of the type. So let's fix that. And let's look also at how software in Spark can interact with the hardware through variables which have a fixed address in memory. So here we have a variable of type integer with a fixed address in memory, which is specified here. And we can analyze it, and we get a warning that says that this is imprecisely supported and that the tool has to assume no concurrent access to non-atomic objects and no writes to or through a possible alias, because indeed multiple variables could have the same address. So the usual thing to do in that case is to declare that the variable can be volatile. That means other parts of the application, whether software or hardware, can modify the value of this variable, which is expected here. And when we reanalyze it, we see that the assumption has been modified. So now it's reporting about possible concurrent access to non-atomic objects and no writes to a potential alias. Because here, if it's written through a potential alias, the analysis will correctly assume that any possible value comes from these writes, thanks to the specification of volatile. Now we can go further and specify that it's atomic, which has an effect on compilation, and reanalyze. And again, here, the assumption has changed. So there's no problem of concurrency anymore because it's atomic. But it's still reporting that there can be writes to potential alias to var. And now we have these 4 fine-grained properties of volatile variables in Spark, and we can specify in particular that there are only asynchronous writers that write into the same memory, but no asynchronous readers. And in that case, now the assumption just points at the correct volatile properties. So the fact that there's only asynchronous writer is correct, which is what we specified here. So after review, we can justify this warning and get the guarantee that we properly took care of all possible behavior. I'd like to finish with how we synchronize this kind of code with the external world if there's some code in C. So we saw the record C struct, and this maps to the equivalent C structure here with an int car and sidecar and short. And we can manipulate that, whether exporting or imported procedures or functions across the language boundary. So let's say that we have a function in C, update C struct that takes a pointer. In Spark, that will be the same with an in-out parameter of the same type. And we'll declare it with convention C and the keyword import with the name that it has in C. It's useful here to declare explicitly on the Spark side which global variables this procedure may read and write, and if it always terminates. So that's the default, but there will be a warning if you don't specify them explicitly because the analysis depends on that. Finally, we can export a procedure or function from Spark to C. So here, if we have this function read C struct, which takes an arg and returns an integer, again, we can declare it with convention C, keyword export, and it's named, and it will bind to this function in C, which takes a pointer. So that's all for this demonstration of using the tool inside VS Code. But I mentioned something. I mentioned that the tool is going to call the compiler to get information about the data representation. But which compiler? In fact, here it uses the right compiler for your targets and runtime because we specified them in the project file. So here that's an ARM compiler, cross compiler for ARM target. And that's what we've been using underneath here. So we've seen that with Spark, you can apply program proof to embedded and systems programs, thanks to 2 techniques. So separation of concerns, where the hardware representation of data and the logical view of data are separated. And in those cases where the hardware representation has an effect on the logical view, in particular in the case of aliasing and typecasting, then we minimize the contact surface. Finally, there are other features that are useful for analyzing this kind of codes, in particular bindings to C programs and the features that allow fine-grained description of volatile data and atomic data. Of course, you have all the contracts that we've seen before, in particular, the latest version of Spark supports contracts for exceptions and termination. If you want to know more, please know that this is only the first webinar in a series of 3. So there will be 2 more webinars in 2024 on proving memory safety and on proving program correctness. And already you can go to the Learn website where we have online courses, and one is devoted to an introduction to Spark. Thank you all.
Thank you, Yannick. So let's go into our question and answer session now. We have some great questions that have been posted. So I'm going to go in the order in which these were received. So the first is from Damien. So this was related to the information that you shared on the rich data.ads file, Yannick. Damien's asking, what's the difference between size and object size?
Yes, size is assigned to a type to say the number of bits that you need for this type. Object size, when given on a type, gives the number of bits that you will use for declaring an object, complete object of the type. But of course, fields of this type, for example, may not need all these bits. So that's for a complete object.
Damien, if you have some follow-up, I invite you to add that to the question and answer. Okay, so then we had a question from Kevin. So Kevin has generated some SVD files using SVD to Ada, and he was asking if you have any suggestions for how to deal with volatile records. So for discriminated records where the error discriminated type cannot be volatile and where component clauses are not allowed for variable length components.
When component clauses are not allowed?
Yeah, if you go to the questions, you can see precisely what Kevin typed. That might be easier than me trying to reread it.
Yeah, so there are some restrictions for the kind of types that can be volatile in Spark. And indeed here, discriminants are not allowed to be volatile in Spark. The issue is that when we access discriminated records, we want to be able to rely on the fact that the discriminant still holds when we're accessing a field, and we don't want that to change arbitrarily. So ideally, you would not create discriminated records of volatile type. I guess that's something to look at regarding SVD to Ada, how we can adapt it to generate Spark code directly.
Okay, and Kevin had a follow-up question for atomic, where two values need to be written at the same time. And Kevin noted that he has edited the XML that's generated to combine them into a single 32-bit value. I'm not sure if that's a question or a statement.
So yeah, I don't understand where the question would be. Two values are written at the same time, like two parts of the objects. Yeah, I'm not sure.
Well, let's set it aside there. And Kevin, if you want to add some detail to that and clarify the question, we can come back to it. So Daniel asks about ownership. So you kind of answered this, Yannick, but maybe you could make it a little bit more explicit. Is there now an ownership model in Ada that's similar to Rust? And Florian asked a follow-up question to ownership. Is it possible to borrow a pointer ownership in Spark?
Yes, so the model for ownership in Ada was indeed Rust. It was the first language to really popularize this notion of ownership, where when you're assigning a pointer to another, you're losing ownership of the underlying data. But what you want to do is that when you're calling a procedure or function, which is going possibly to only read or read-write the pointer, you don't want to have to explicitly return the ownership when you return from the program call. And so that's where borrowing occurs. So when you call a function or procedure, you can borrow the underlying data in the pointer. And the same holds true for loops. So you are able to go over data structure, in particular recursive data structure, with a local borrow. And so the terms that we use in Spark are an observe when you're just reading the underlying data. And we use special syntax for these local observers and borrowers. So we use unnamed types, so unnamed access type, where you declare the variable, local variable, which is going to borrow or observe a data structure with directly access and the underlying type. And so you have more information on that in the Spark Users Guide with examples.
Okay, great. Thank you, Yannick. Damien had a follow-up question about size versus object size. Damien, Rod answered this in the chat if you want to glance at what Rod said. But Yannick, do you want to say a few more words about why you would prefer to use size versus object size?
Well, size is exactly the size of the type when you're going to use it everywhere. So as a field, as the type of a declared variable. Object size only applies to the size of the object, the full-blown object that you declare. So in general, for Spark, size makes more sense because you're going to use the type, for example, in as a component in other types. But you may use both.
Okay. Sorry, I'm finding it slightly chaotic to jump between the questions and the chat to look for questions. I apologize. Please bear with me. We have a question from Tamas. Must the constraints on sizes of data rely on compile time constants, or can predicates on subtypes rely on variables?
Yeah, so there are two questions. So the size of data might depend on runtime values, but some expression that you use in your program. So for example, when you specify the size here, that must be a static value. So that's mandated by the language, by the Ada and Spark languages. But the size itself may not be known. So if you have a variable whose bound, for example, are computed at runtime, indeed the size is not static. Again, you may want to specify the size or alignment, object size of your types and objects. Or now you can rely, with the latest version of Spark, on the underlying compiler to compute that. And the analysis tool is calling the compiler to get this information. And the second question was about predicates. So predicates on types cannot depend on variables. That's a constraint in Spark that for a lot of the assertions that they must be kind of self-contained. And here, we don't want a predicate on a type value to be broken by modifying a variable somewhere else. But in many cases, you can also just, if what you care is the value of this variable at the point where you describe the type, you can just introduce suitable constants at this point.
Okay, there was a question about whether the webinar would be available to rewatch. So for those of you who might have joined a little bit late, an email will come out as soon as the webinar has concluded, and that email will include a link to the video recording of the webinar. So you'll be able to see the entire webinar and the entirety of the Q&A session. Valentine asked whether the demo files would be available. These are not going to be sent out as part of the email. However, if you would like to receive the demo files that Yannick used during today's presentation, please reach out to info@adacore.com or reply to the webinar email that you're going to receive and request the demo files that way. And then someone from Adacore will be in touch with you and we can make those demo files available. Derek asks, how do you select a prover when you run Spark?
So here, there are various switches at different levels when you are calling Spark. So CNAPROVE, really the analysis tool. There's a switch, the high-level switch called level, and you have values of level between 0 and 4, and these decide on a number of lower-level switches, in particular, which provers are called. And of course, the higher the level, the more provers we use. Otherwise, you can use directly the prover switch, which is a list of provers, so from 1 to all the provers that UnitedProof provides, so AlterGo, CVC5, Z3, and Colibri. So you can specify all as a value to call them all, or 1 or 2 or 3 of these.
Okay, Chris asks about facilities for interacting with C++. So you showed some C bindings. What about, for example, template-heavy C++?
Yeah, so here we really rely on the facilities in Ada for interfacing with C and C++. So that's possible with C++, but in that case, the name mangling is quite complex, and then you have to find the names for declaring these external names that I showed. So definitely, it's much easier with C than with C++. And with C++, you might also get more difficulties with aberrant codes and other specificities of C++. So C is the preferred path, indeed.
Mohammed asked, what's the difference between a target and a runtime? I think this is related to your showing the GPR file.
Yes, so the target is really the hardware platform, like ARM, and the runtime is the library that we choose to ship with your program. In Ada, you can choose different runtimes. So that provides for embedded platforms the embedded runtime and the light runtime, depending on the platform, also the light tasking runtime. So some level of tasking, but not all of Ada. But only for native platforms, you have the full runtime of Ada with all facilities for interfacing with the file system, for example, and using all the tasking facilities and concurrency facilities that you have in Ada.
Gabor asks, how well do the provers scale? And if we have an idea of the size of programs that can be proved without timeouts? And before you answer that, Yannick, it is possible to play around with Spark. First of all, you can go to learn.adacore.com and you can interact with Spark there in the context of that website. You can also reach out to sales through info@adacore.com, and through conversations with sales, an evaluation could be provided to you so that you could try it out.
Yeah, so the question is...
how well do the provers scale?
Yeah, so really, the provers are called only on individual functions. So you don't have to worry about your program being big, but about your functions being big. So one mediation is always to make smaller functions so that the context for the proof is smaller. But that's something that you also discover because there's no linear relationship between the size of the code and the proof time. It's really related to complexity. So that depends what kind of code you're writing and what kind of properties you're trying to prove. So really here, you can try with the tool and adjust based on what time you accept to wait for the answer from provers. You can also use this timeout switch to define how much time you want to wait for each prover, knowing that when you run now multiple provers, they will run in parallel. So if you have a multi-core machine, the first prover to find the proof will allow stopping the search for this particular proof. So it's quite efficient on multi-core machines.
So we have time for one more question, and I'm going to arbitrarily pick one. So Mahasura asked, how does the ownership principle in Spark ensure data integrity and prevent race conditions in concurrent or multi-threaded environments? Can contracts help in this kind of case?
Yes, so indeed, the way that we've been using ownership in Spark is mostly to ensure that formal verification is possible so that you don't have this kind of aliasing, which defeats simple application of the principle of proof. But that's still possible to use it for concurrent code because there's support for concurrency in Spark. So that's a limited subset of the concurrency features that you have in Ada. There are profiles, so that's called the Ravenscar and Jarvik profile, which define static configurations for tasks and protected objects. And protected objects are these log data structures implemented in compiler that protect data that you want to access through different tasks. And these data, if it contains pointers, you will have to comply with the ownership ownership properties when you, for example, you assign a pointer to such a predicted object or get such a pointer from a predicted object, so that indeed, when it's inside a predicted object, it cannot be shared outside freely. And if you try to access any data, whether it's a pointer or just regular data, outside of these predicted objects or atomic objects, what we could synchronize objects in Spark through different tasks, you will get messages from the tool that report that there's a possible rest condition here.
Okay, we're at the end of our time box. Thank you everyone for coming. If I didn't get to your question, we've certainly taken note of your question. Please reach out to us and we would be happy to respond by email, or we would be happy to set up a follow-up call with you so that we can answer your question directly. Once again, thank you everyone for coming. Really appreciate all of the interactivity, and I hope to see everybody at the upcoming next webinar, which will be at the end of January. Thank you all.
Thank you.